Hello everyone, my name is Burcu. Today I want to talk about Escher, which is a middleware to support principled and modular design and deployment of multi-tiered cloud systems. Distributed systems that are deployed today on data centers consist of dozens of interacting individual services. This is an example architecture of a social networking application we may find running on the cloud. Services in these systems interact non-uniformly and non-trivially with each other, where most services act both as servers and clients. For example, here, the Redis service acts as a server for the user timeline service, as this service relies on it. At the same time, the Redis service is a client of the MongoDB service. Each of these three services, or other services in this architecture, may be deployed in a distributed fashion. Additionally, services can be grouped together based on the functionality they provide for the application. For example, Memcached and Redis are services that are used for caching, so we may group them together as the caching component. Similarly, we can group the MongoDB instances together as the storage component and the index services as the indexing component. We can group other services based on their function and interactions as well. For example, we can have a post management component and a load balancing component. The higher level components of services interact with each other, and they can further be grouped to form the main front-end, application logic, and data tiers as shown in this figure. Finally, these tiers together make up the social networking application that the orange client interacts with. So in the end, what we have are these complicated distributed systems of distributed systems, where components at any level of specification highly interact with each other. There are several challenges in handling such systems. First of all, as different components have different non-functional requirements, they have different deployment needs. For example, the caching component may need to support sharding to deal with high load, whereas the storage component may need to support replication for fault tolerance. Secondly, these requirements may change over time. For instance, the number of shards may be adapted with respect to the load, replicas may be added or removed, and clients may come and go. What we need to deal with these challenges is a clean abstraction for the interaction between any two components at any level of specification. So what we need is an abstraction for the interaction between any two arbitrary distributed systems. Such an abstraction allows for components to be specified, verified, and replaced modularly and independently. Let's take a closer look at the design properties that our abstraction should support. Consider two of the components in the prior example. If these components are standalone services, there are many existing methods we can use to allow them to communicate uniformly, regardless of the programming languages they're implemented with or the platform that they're deployed on. These solutions include RPC frameworks like Apache Thrift, enterprise service buses, and message queues or streaming services like RabbitMQ or Apache Kafka. As we saw, in reality, components are likely distributed. For example, assume that the server in this case is in fact replicated. Firstly, this type of transformation should be transparent to the client component. That is, the client should not know that the server is distributed. This is so that the two components can be developed and deployed independently. For the specific case of replication, there are some existing standards that provide this property, such as fault-tolerant Corba. However, we are looking for a general solution that can support any kind of transformation. For instance, the server can be sharded or load balanced instead. Our abstraction should also work for these types of refinements as well as replication. Moreover, as we saw in our social networking application example, interactions between components in a cloud system are non-uniform. Specifically, the client component itself may be distributed as it can act as a server for another client. For such cases, we want the transparency guarantee to be two-sided. There is no existing solution that provides this type of transparency for any kind of transformation. Escher provides a transparency property so that the transformation details of any component is hidden from any unrelated component. In addition, because of the different objectives each component may have, we want to support transparency for any kind of transformation. For example, we may have a replicated client interact with a sharded server. Escher supports generality, such that a component can be transformed in any way. Finally, using transparency and generality, Escher can also provide flexibility, such that any component can be replaced without the need of reconfiguration or recompilation in any other component. To summarize, Escher is a middleware that can be used to build and deploy distributed systems of distributed systems with transparency, generality, and flexibility. Now that we talked about the motivation behind Escher and the properties that Escher needs to provide, let's go into the design. I want to first talk about the building blocks of Escher. An Escher system is composed of a collection of agents that communicate using a message bus. The agents in the system implement components. An agent can be refined, that is, it can be replaced with one or more agents. The refinement is correct if the new agents have the same external behavior as the old agent. A common example of a refinement is sharding. Let's assume that we have an agent with partitionable state, like a key-value store. This agent can be replaced with two new key-value store agents, where one store takes care of processing keys with odd parity, and the other store processes keys with even parity. Refined agents can also be refined again. For example, a shard of the key-value store can be replicated for fault tolerance. Agents use the message bus for communication. The message bus is responsible for carrying a message from a source agent to the destination agent. The message bus is also responsible for hiding the refinement details of the source from the destination. Thus, it provides the transparency property that we discussed before. Now, I want to talk about some of the design challenges that we've solved through the lens of the design properties that they're related to. To provide transparency, the message bus needs to know about the refinements of agents. It additionally needs to enforce isolation, so that agents can only communicate through their exported interfaces. To provide generality, the message bus needs to support transparency for any refinement. Some key questions to answer here are: what information about the refinement of a source that the message bus needs to hide that refinement from the destination? And how can we formalize this information such that it can capture any refinement? To provide flexibility, we need to think about the deployment and management of agents, particularly about how we can achieve these in a modular way. Moreover, to continue supporting transparency and isolation when malicious or arbitrary behavior happens, we need to think about how to achieve these properties in a secure way. Additionally, we need to implement the message bus abstraction in a fault-tolerant way so that it is not a single point of failure. Before addressing some of these challenges, I want to first take a minute to talk about composition of agents in Escher. An Escher agent consists of a state machine, an inbox and an outbox of messages. Each agent is identified by a unique identifier, which in this example is S. The agent can be refined as described previously. In this case, the original agent is called the parent agent, and the new agents are called the child agents. Multi-level refinements lead to a hierarchy of agents, at the root of which is the system agent, which represents the entire system. Now that we know a bit more about agent composition, I want to talk about how the message bus provides transparency and generality. The responsibility of the message bus is to take a message from the outbox of a source agent and place it in the inbox of the agent that the message is destined to. If neither the source nor the destination is refined, this functionality is straightforward. Now assume that the source agent is refined into a number of child agents. From the destination's point of view, communication through the message bus should be identical to communicating with the parent agent S, as if there was no refinement. So the destination expects to receive the red message that is at the top. However, it is possible that that message itself is not sent by any of the child agents. This would be the case for some refinements, such as erasure coding. The message bus needs to construct the topmost red message from S using the messages in the outboxes of the child agents. In general, for a correct refinement, we know that there's a deterministic mapping from the outboxes of the child agents to the outbox of the parent agent. For example, in the case of Byzantine fault-tolerant replication that can tolerate F failures, F+1 messages from child agents with matching payloads would map to a message from the unreplicated parent agent. We call this mapping the merge function of the refinement, and it is the piece of information that the message bus needs from a refinement to provide transparency. Another key requirement to providing transparency is ensuring that agents can only communicate through their exported interface. For this, we need to think about which agents are allowed to interact with each other. A correct agent can only communicate with agents that it knows about the existence of. So whose refinements are known to a specific agent? An agent knows about its sibling agents as they're part of the same refinement. It also knows about any agent that its parent agent knows of. Therefore, the Escher message bus allows an agent to only send a message to its siblings or any of its ancestors' siblings. To enforce isolation in the presence of malicious agents, we need to provide authenticity. Escher needs to guarantee that an agent cannot forge messages that are seemingly from another agent. For this, Escher includes a public key infrastructure. I will talk briefly about how this works. Every agent in Escher has a manager. The manager for every non-leaf agent acts as a certificate authority, and it issues public key certificates for the child agent of the agent that it's managing. The manager of the system agent is a trusted root certificate authority. These certificates bind the identifier of an agent to its public key and refinement, so agents cannot lie about their identifiers or the merge functions of the refinements that they're part of. Finally, certificates are chained. Certificate chains are attached to outgoing messages to prove the identity of the sender. In terms of deployment, the manager of an unrefined leaf agent is the runtime that runs the implementation of the agent on a physical machine. The runtime is also responsible for attaching certificate chains to messages. Here, we denote the runtime as the pink boxes. So far, we've only talked about the design of Escher. Implementing abstractions with such general and powerful guarantees poses its own challenges. I want to briefly talk about how we handle the implementation of merge functions and the message bus. Since we want Escher to provide generality and support any refinement, we want to support implementations of arbitrary merge functions. The challenge with this is handling malicious agents that can refine themselves and construct malicious merge functions. For example, here, agent XY can refine itself and construct a merge function that leads to infinite loops or unsafe system calls or commands. Some possible solutions are using sandboxes and constructing safe domain-specific languages. We leave exploring these options to future work. Currently, Escher implements merge functions with a limited DSL as a map of commands to values. The command describes an action that the runtime should take to merge a message, and the value customizes this action. For example, we have a command wait for matching that asks the message bus to wait for a certain number of messages with matching payloads. Another command from specifies the identifiers of the sources that the messages may be from. These two commands allow Escher to support a variety of quorum-based replication methods and sharding protocols. For example, the merge function of a replicated agent that can tolerate F Byzantine failures is implemented with the two command value pairs, wait for matching F+1 from the identifiers of the replicas. For this specific example, that corresponds to the pairs wait for matching with a value of 2 and from with the value of the listed child agents. I want to now talk about how we implement merging at the message bus. First of all, the message bus abstraction is implemented in a distributed fashion by runtimes. In addition to running the agent, the runtime of an agent communicates with other runtimes to implement the functionality of the message bus. The first question about merging we need to answer is where it should be done. Outgoing messages could be merged at and sent from the runtime of one of the child agents of the source, a proxy. This is intuitive because the child agents are already part of the refinement, so they know about the merge function of the refinement. However, this approach is not fault tolerant and adds an extra communication step between runtimes. Another option is merging messages at a reliable and trusted middle service. The service would need to be replicated for fault tolerance and can become a bottleneck for all communication in the system. It also adds an extra communication step as well. In Escher, messages are collected and merged at the destination's runtime. This introduces no additional reliability assumptions or communication steps. However, the destination runtime needs to learn the merge function of the source agent. To implement merging without extra communication steps or reliance on middle services, the runtime of a source agent piggybacks the merge function implementation of its refinement to messages that it sends out. We call this tagging. The runtime of the destination collects and groups messages and uses the attached tag to run merging. Once merged, the runtime can place the message into the inbox of the destination agent. There are many interesting parts of Escher that I did not get to in this talk. These include wrapper agents that Escher provides that can take the implementation of an agent and deploy replicated or sharded refinements automatically. How Escher handles agent discovery and runtime-to-runtime communication. How Escher handles tagging and merging with multi-step refinements. How Escher provides garbage collection so that the inboxes and outboxes of agents do not grow indefinitely. And how we would provide support for legacy services so that they can be deployed with Escher gradually. To conclude, using Escher, we can build and deploy distributed systems of distributed systems uniformly. Since Escher provides generality, these systems can be specified in any way. With Escher's transparency guarantee, we can isolate these systems from each other and handle them independently. And finally, we can evolve these systems over time without any trouble. Please see our paper for more details.